Hello everyone and welcome back to the Geoscientists Voices. Today we are exploring the final frontier through the lens of a man who listens to the pulse of the planet. From tracking fallen space debris with earthquake sensors to searching for water on the moon, our guest today bridges the gap between the laboratory and the Mission Control Center. Joining us is Ben Fernando, a Postdoctoral Fellow at Johns Hopkins University in the USA, a member of multiple NASA science teams, and a sub-lieutenant in the British Royal Navy Reserve. Ben, thank you so much for being here.
Thanks for having me.
Ben, your work at the intersection of NASA missions and high-performance computing. Was there a specific moment, perhaps growing up in Birmingham or during your early studies in Imperial, where the connection between geophysics and space exploration clicked for you and you knew this intersection is where I need to be?
I think during my PhD, there was a point where it became clear that a lot of the techniques that we were developing for seismic modeling on Earth to try and understand how seismic waves propagate in the ocean, to try and understand how the ocean affects those waves as well, I realized that a lot of that could be applied to studying Mars as well as part of NASA's InSight mission. And that I think was one of those click moments that you see many of the links in physics between what we'd been doing on Earth and what we were trying to do really for the first time on Mars.
Wow, that's really, at the same time is obvious, but not so obvious intersection and connection. And it's great that you found it and explored it. So, moving from your PhD at Oxford into high stakes NASA research is a massive leap. What was the biggest hurdle, professional, mental, or political, you faced in that transition, and how did overcoming it shape your outlook as a researcher today?
I think one of the tough things about doing mission work is figuring out how to bridge the gap between pure scientific research, either that feeds into the concept design of the mission or experiments, and the results at the end of it. It's not like going into the lab on your own and being able to go from an idea to an answer just working by yourself. There's a huge number of other constraints, other people's research, other people's priorities, the mission's research, the mission's limitations that you have to work within. And, you can push some of them, but at the end of the day, they all have to be accommodated to some degree or another. And I think for me, that was a good learning experience to understand a little bit more of, I guess, the operational side of research, how what I wanted to explore could fit in with what was possible in a very specific and quantifiable way. And of course, the way that you do that is by having a supportive team of colleagues who have more experience and are able to explain and demonstrate that process as they go. It's not always, I would say, obvious or trivial to balance those conflicting priorities, especially in, planetary science work where we often have a complicated interplay between power and communications and instrument time, etc.
So, following up on this question, do you have like some ideas that probably maybe don't fit in today's work of your lab or like in current state of development of the science that you probably have in your mind, but probably will be only able to start working on like in 10 years time or 20 years time, something like that?
I mean, one of the big things that I was very interested in on Insight was understanding the rate of impact processes over time. So we have these meteoroids that come in, they strike the surface,
Mhm.
they create craters. The number of those craters tells us about the age of surfaces. They obviously play a key role in shaping the evolution of planets as well. But Insight offered us an opportunity to study those processes almost in real time by discriminating between tectonic Marsquakes and impact-driven Marsquakes. We saw maybe 10 or so confirmed impact Marsquakes, and there are probably more as well that we haven't identified yet. But part of the challenge is that that data set is in some sense complete. We have as much as we are going to collect, at least for the time being. So there are many more questions to be answered. Obviously, there's more to be learned from the data, but it's not like there's more data being collected now, and there probably won't be more data being collected for several decades. So in the meantime, we can keep researching it, but designing new research questions inevitably involves better, more data, and that's not really where we are at the moment, which is unfortunate, but kind of the way it is, I guess.
Oh, well, good luck in exploring these questions as soon as possible. I really wish you luck in that. And now I want to talk about your recent article published in the high-ranking journal Science. In this article, you talk about tracking space. Namely, you caught a 1.5-ton Chinese satellite, Shenzhou 15, re-entering the atmosphere, and it was nearly 30 kilometers off from where NASA thought it would be. How dangerous do you think it is to lose control over giant objects in the sky, and how did you use common earthquake sensor to find it?
So we knew from our work, both on Earth and as part of InSight, that these re-entering objects shake the air, they shake the ground, and we can use those detections of sonic booms to characterize the trajectory of these objects to understand a little bit more about what direction they're coming from, what direction are going in, what speed they're going in, how they're breaking up. And the big step here for us was to apply that methodology from natural objects to artificial objects, that is, space debris. Now, of course, we have this problem that you've highlighted that these reentries keep happening. There was one over the weekend on Friday of an object that was much bigger, a spent rocket stage, again from China, several tons that broke up over, we think, the southern Pacific Ocean. And these things are basically uncontrolled. They come down where they come down. In the vast majority of cases, that process isn't controlled. As for the implications, we've seen many times already cases where debris has fallen in spots that we're not expecting it to, or indeed, places where the impacts of that debris have had a substantial effect on other processes. So, for example, during the spring of last year, we saw several explosions of SpaceX's Starship rocket, which caused debris to fall out over the Caribbean, caused multiple flights to have to undertake diversions, etc., etc. So it's a real problem and a going problem that I don't think anyone necessarily has a handle on yet.
So the follow-up question is, what do you think is more dangerous for humanity, falling debris, created by man-made structures like satellites, or meteors or comets, or I'm not sure how to call them, but which are basically not made by humans?
Yeah, I mean, I guess they're opposite ends of the spectrum. The space debris is frequent and it's relatively small in the grand scheme of things. Meteors pose a risk, but there's never been a recorded case of anyone being killed by a meteor. They've been around for much longer, but equally, asteroids have clearly been responsible for at least one, maybe multiple mass extinctions in Earth's history. So, in that sense, I guess natural objects pose a bigger risk. It's just that the risk on a day-to-day human-to-human level posed by large asteroids is pretty small at this point in the Earth's evolution.
So do you think something that mass extinction where dinosaurs were supposedly killed and many other creatures, will it happen in our lifetime, do you think, and maybe a couple of generations in?
I mean, I think at this point we expect um, mass extinctions caused by impact events to maybe happen once every 100 million or so years. So in that sense, it's unlikely. But of course, these are random processes, so there's no determinant. There's nothing to say that this year is less likely than next year or the year before.
Oh, that's your opinion is from one side it's positive. So I will keep this tone in my head. Uh, you also mentioned breaking up of satellites, and you described it in your article as not one big boom, but as a cascading failure, almost like a waterfall of fire. So if we could actually hear that with our ears, what would a dying spacecraft sound like?
At any one point on the ground, you normally record a boom. It sounds like a gunshot. It's in fact much of the same physics going on there, which is basically the passage of the shock wave over your ear. And that shock wave includes two parts. There's the compression, so that's all the air molecules basically stacking up at the front of the shock, and then the rarefaction that follows. That's a low density pulse. Um, with the sonic booms, the spacing between the sonic booms, the amplitude of the sonic boom depends on a lot of factors, including the size of the object, its altitude, its speed, etc. So, trying to understand exactly how that boom would sound to a person is an interesting question. It probably depends how far away you are as well, what altitude you're at, and of course, how the object is breaking up. In general, it probably sounds like a thunderclap or something like that.
Wow, it's an interesting insight, and I wanna come back and talk about the system using like Mars quakes that you described a couple of questions ago, and about scaling it up. So in the future, do you see this becoming a real-time system and maybe widely applied? And could we actually use these ground vibrations to send out local alerts to the exact spots where debris is about to land?
So the thing is that we can't use the system for early warning in the sense that because the objects are supersonic, they're always going to outrun their own sonic booms. But what we could potentially do is use this system to figure out where debris has landed very soon after it's happened. So if it's containing material that, for example, is toxic or flammable or environmentally sensitive, being able to characterize that location within the first few minutes after an event is a big advantage over taking several days to do it. And that's the difference that we're trying to achieve here.
Well, good luck in achieving this very important milestone. And I want to move forward to another facet of your research, because you are a science team member for the Viper rover, which is specifically designed to hunt for water ice in the moon's permanently shadowed regions. Your role involves running high-performance simulations to understand how seismic waves move through the lunar soil. So is it fair to describe this as a sort of a form of high-tech treasure hunting where you're essentially using a seismic stethoscope to find where the water is buried without having to dig up into the entire moon?
Yeah, that's a very good description for it, actually. So we suspect that where there's ice at the south pole of the moon, in these regions where the sun has never shone for billions of years, there is probably liquid, solid water frozen into the regolith, so the surface of the moon. And we expect that the presence of that water, how much it is, what form it takes, etc., will change the seismic properties of the regolith. And so we're hoping that we'll actually be able to hear the difference between the dry regolith and potentially these icy regolith patches in the permanently shadowed regions.
Oh, sounds great. And pardon me for a naive question, but what this water is going to be used for, and how do you think it's going to be produced? Like, will it take a lot of time to do that?
So there's a lot of potential uses for water that go beyond just drinking it. It's also useful, for example, for radiation shielding. So the moon doesn't have a magnetic field. It experiences a pretty substantial surface flux of radiation from the sun and from cosmic rays in general. That water is a pretty good absorbent of radiation. Similarly, you can split it with sunlight into hydrogen and oxygen, which is rocket fuel. But it shouldn't be underestimated. We're not talking about the Antarctic. There's not huge sheets of ice, we don't think, buried under the south pole of the moon. It's much more likely that there are small pockets of water scattered in small grains or sort of adhered to sort of the sandy regolith particles that we have there. So it's not going to be trivial to extract it. It'd probably be quite a advanced operation to try and get at all of that water stored within the lunar interior.
Oh, wow. Thank you for this insight. And let's keep talking about the moon, because the timing of this conversation is incredible. Because this week or the next one, the Artemis 2 crew is scheduled to make their historic flyby around the moon. While they're looking down from the capsule, you are looking at the data from the ground. So, from a geophysics perspective, what exactly are you listening for for that could tell NASA if a specific site is stable and safe enough to build a permanent human base on?
So there are two major sources of seismicity on the moon. One is moonquakes, and they have different origins, sort of some are thermal, some are tidal, some are other probably remnant tectonic processes. And it's probably those remnant tectonic processes that pose the biggest hazard to astronauts on the surface today. The other hazard is, of course, impact events, and those are random, so they can happen anywhere on the surface, anytime. In terms of geophysical understanding, what investigations of the seismic properties of the moon can help tell us is how strong the strongest moonquakes are. We don't think that they occur randomly over the surface, just like on Earth. There's probably regions with more moonquakes and regions with fewer moonquakes. And of course, as well, we don't just want to know how strong the moonquake was where it occurred. We want to understand how much it shakes the ground further away, because some of these moonquakes are probably strong enough that you would want to avoid some of the adverse consequences of having the lunar regolith shaking around you.
So I've actually heard that I'm not sure if the site for landing is defined. On that I did not follow the news, but I've heard it's going to be on the border between the shadow and the lighted zone. So basically, a lot of things should come into like interconnection. Like it has to be this shadow, light zone, and no earthquakes. So it's like basically a perfect spot, which is like pretty rare to find, right?
So, yeah, we've never actually had a seismometer at the South Pole of the Moon before, so we don't really know anything about what that environment will be like. It is, as you say, probably very complex. The thermal effects from moving out of permanent shadow into very bright daylight are probably substantial as well.
Wow. Wow. Interesting. And are they actually plan to put seismometer on the South Pole?
Yeah, so the Farside Seismic Suite will be going to the South Polar region, and the Lunar Environment Monitoring Station will also be going to the South Pole of the Moon.
So do you think this data will be open or only closed to NASA
No, so
people?
NASA's data is all made public, normally with a 3 or 6 month delay after it's collected.
Wow. Wow. I think that there's gonna be like myriad of articles about it, and I mean that's truly gonna be great. I didn't know that, so I'm just like
Yeah.
excited about it right now. So, looking even further out, you're also on the team for the Dragonfly rotorcraft mission to Saturn's moon Titan. Titan is a truly alien world with an atmosphere, as I heard, like with atmosphere, organic chemistry, and even lakes of liquid methane. So, if you could drop one of your sensors into those exotic methane oceans or onto its icy crust, what is the weirdest or most unexpected thing you're hoping to hear?
I think what would be really exciting is if they do exist, if we see any evidence of hydrothermal processes on the seafloor. So there's this global ocean potentially on Titan, and at the bottom of that, there may be, there's certainly no certainty, but there may be links between the deep interior and the ocean in the form of sort of hydrothermal vents that occur in the ocean on Earth. Those would be really interesting from a seismic perspective. They'll probably produce sound, which we may hear, but also very interesting from a perspective of astrobiology, because those are the sorts of environments where it potentially seems more likely that life might actually one day evolve.
Wow, but not now, but in the future, right?
Or maybe has in the past. It could be either.
Wow, yeah, there are so many things we don't know about space. It's just crazy. Uh, so let's let's move into more like personal facet of your life because I think it's this information is going to be interesting for me for sure, and I'm sure for our viewers as well. So you've been through two very different kinds of intensity: officer training in the British forces and defending your PhD at Oxford. So be honest, Ben. Which was actually harder, surviving military training or defending your thesis to a room full of experts? And the follow-up question is, how does being a naval officer actually make you better at NASA when a million dollar robot, let's say, is failing or malfunctioning on Mars? Does that mission first military mindset help you lead the team through the crisis?
Yeah, good question. I think they're challenging in different ways. A PhD is a long slog. It takes 4, 5, sometimes even folks take 6 or 7 years to finish. And there's not necessarily obvious progress that's made on a day-to-day basis, but equally, there's a lot of freedom that comes with it. Military training is quite the opposite. There's progress on a day-to-day basis, and it comes with basically no freedom to do anything. So, in that sense, the military training is definitely harder. It's much more physically demanding, but it probably doesn't involve nearly as much thinking or nearly as much creativity. So, they're difficult in different ways. But I think there are lots of overlaps as well that you hit on. The planetary science that we do is mission focused and it's very procedural. So we have science questions which are obviously creativity driven, but they can't be answered with necessarily a creativity first approach because we have to work in terms of all those previous constraints we talked about: power, communications, budget. So I think that the key thing to learn and take away from military experience is understanding how to work within a team in that mission focused lifestyle, whilst also having to deal with all of the constraints and procedures that you have to follow. And for some people, that's a source of huge frustration, that they can't just do whatever they want whenever they want. But equally, that's the reality of how these missions operate. So I found it quite useful to see mission operations through that lens on occasion.
Wow, that's great that it actually helped you even in such a creative environment as science, where the strict procedure is, as I see now, is also in place. And now, like keeping talking about your the personal facet of your life. So I want to talk about the advocacy that you also did, because you successfully fought to abolish graduate application fees at Oxford because they were elitist. So please tell us more about it. And also, what is the biggest lie people believe about who belongs in spaces like Oxford and or NASA, and who doesn't?
So I think the reason that we push so hard for that is this belief that graduate education should be inclusive and open to everyone. And I think most people agree with the sentiment, even if the realities of how that works out in practice are not always obvious. Um, I think this, leads to the second part of your question quite nicely. There was clearly a mindset in the past of who belonged in those spaces. I'm not sure there is a template for people today in terms of how they belong or don't belong in those spaces. Fundamentally, when we have students who want to come work with us, we're not looking for someone who looks or thinks in a particular way. All that I'm particularly looking for is curiosity and the skills that they've developed from applying their intellect to solving problems that are difficult in the past. So I think that there's a lot of work to undo and even thinking that there's a specific kind of person who belongs in either space today. That's not to say that there's not still remnants of that discrimination or stereotyping, but hopefully it's better than it was in the past.
But when you were fighting for it, weren't you afraid that it might backfire and like affect your career in some negative way when you were trying to fight against that
Yeah,
elitism?
I mean, it's always a possibility. I think if you go through life spending too much time worrying about that sort of thing, you probably don't make any particularly effective change in these areas, though. So sometimes if you have the privilege to be able to address these questions, I think it's important to do so.
Well, well, thank you so much for doing that. I think it relates not all only to planetary sciences or NASA, but generally to all the sciences, and you made a great effort to actually correct this injustice. Uh, so, but let's say that there is like a student who watched this interview and he or she like they think that they don't look the part of a space scientist. So, what is one move or they should do or advice that you can give them today to crash actually the gates of this so-called ivory tower of space sciences, Oxford, NASA, etc.?
I think at the end of the day, regardless of what structures or barriers are in place, we all have to make our own space in these institutions, in these teams that we work in. And I think it can be challenging, but I'd always tell people, especially in a mission concept, don't be afraid of trying to make your own space. And that doesn't mean that it necessarily has to be a one-person thing. It doesn't have to be dominated by ego, but carving out what works for you, both in terms of how the missions operate, but also in terms of what you're working on and how you interact with other people is very valuable.
So, like, building your place means that you have to stand your ground, or that you, I mean, have to establish your own field of research. Can you, like, clarify a bit
Well, I think
for me?
sometimes it means that. Sometimes I think it just means adapting what it is that you want to work on to be within the constraints of what's actually available on the mission or within the team. Sometimes it means building a space where other people are included in a way that you wish you had been in the past. I don't think it necessarily has to be confrontational, though, of course, there are cases when it does become so.
Yeah. Wow. That's a great advice. Thank you so much. And other viewers, I think, will take it to heart. So I mean, your life like has a lot of facets from British Defense Forces to like building this inclusiveness for other students, and of course the space sciences. So I think, at least for me and for you, I think maybe as well, it would take a lot of energy to accomplish all of it. So to keep your creativity at a high level, what do you turn to for inspiration outside of the lab? Like, what personal hobbies, maybe a book not only about science, but about something else. What actually help you to get this energy going?
Yeah, I spend a lot of time outside, mostly running. It's a little bit hard right now because it's pretty snowy and icy, so that's a bit depressing. But yeah, for me, I think that's something that always helps to recharge. Obviously, other people have their own areas, but I think that exercise and being away from my desk and emails really helps.
Oh, that's uh, that's great advice. I should do that sometimes as well. So maybe I'll start doing that tomorrow, thanks to your advice. uh, so you're in the USA now, and imagine that Hollywood calls to make a movie about your life. Do you want it to be a space seismology thriller or rather a NASA action movie?
Definitely the space seismology.
Wow. It's hopefully, and I'm sure that there is a high chance that this movie will be made. I will buy the ticket to go there
Thanks.
and watch it. Yeah. Uh, and finally, Ben, in just one single word, how do you describe the future of geosciences?
Exciting.
Yeah. Uh, is it like the most exciting thing for you? Like something that drives you more than
I think
running
so.
and yeah, yeah.
At least right now. Yeah.
Wow. Good. Well, thank you so much for sharing your journey with us today. And it was really insightful, and it is truly inspiring to see how geophysics can help us not only explore the stars, but protect our own planet from falling hazards. I wish you all the best in your current and future research projects.
Thank you.
And thank you also to our viewers as well for joining us on Geoscientist Voices, and see you in the next episode.